3.3.1.1 progressive waves, where we shall do oscillation of particles in the medium. Amplitude, frequency, wavelength, speed, phase, and phase different, where wave speed is equal to frequency times wavelength, where frequency is 1 over the time period. Phase difference may be measured as angles in radians and degrees, and as fractions of as a cycle. So yeah. Now, okay. Now what's the first thing we do? Well, a wave is the oscillation of particles. So a wave is equal to the oscillation of particles. So how particles vibrate through a medium. Um, okay, now what is a progressive wave? A progressive wave carries energy from one point to another. You can take that as a wire carrying energy from one side to another, however you want to see that. But it does not doesn't transfer any material. Again, you're charging your phone, you're just taking the energy from the source and giving it to your phone. No material transfer, just energy. Or electricity, but electricity is also just energy. A wave is caused by something making the particles or the area oscillate from the source, and since from the source it's vibrating, it vibrates everything around it. So from the source to the end point it vibrates, and as it is vibrating it will carry energy. So if we have the source generates energy or produces energy or gives it energy in some way or form. Now this moves over here, but that means everything around it will start moving, so it will move that way, that way, that way, and of course no energy no material is transferred, because that is moving that, and that is moving that over, like, so this point here moves this point here, which moves this point here. It just moves the points, but does not actually move the points to another place, just moves the points, which is the energy transferred. Okay. How do you know? Oh, one second. How do you know a wave is equal to? How do you know a wave is carrying energy? How do you know a wave is carrying energy? Well, um, electromagnetic waves, or EM waves, they can heat stuff up. Now, the only way it can heat stuff up is, of course, if it has energy to transfer into the atom, which makes the atoms vibrate more, making it hotter as they collide against each other. X-rays and gamma rays, they can cause ionization. Now, if it is able to cause ionization, that means it's exciting electrons. And of course, if it's exciting electrons, it means that the electrons gain energy. So, of course, it has to carry energy. Um, there are more examples. I will go through all of them actually. Why not? We have the time. Um, Wave powers, so like hydroelectric dams, they take water waves and convert it into electricity. That means, of course, the water waves carry energy. And finally, one thing to keep in mind, it's not an example, but whenever you are transferring energy from the source to your to whatever it's transferring it to, the source has to lose energy because it is giving off energy. That means there must be something, some energy that it loses. So that is how you know that a wave carries electricity or energy. Now, we need to know how a wave works, or how it looks like basically. So for that, we will set up a wave. Let's say that goes down, and it goes up and down and up and down and up. It goes up, down, up and down, for example. Now, in this one cycle refers to the same point on the wave. So, cycle, same point along a wave. So what does that mean? One cycle from this point. Now this matches here, but it's not the same point, as this is going upwards and this is going downwards. That means the same point would be this over here and this over here. These are the same points across the wave. This could also be this point going down and this point, so I'll draw that in colors. So this point here would be the same as this point here, or this point here would be the same as this point here, as they both are doing the same thing in the same direction. So they're the same point. Secondly, we have the displacement, which is pretty simple. It's just this one over here. So how far the wave is from its original point. So this is origin. That means this is positive displacement, and this is negative displacement. Or, well, I'd rather say S for short, because displacement. In waves, it's actually x. I mean, you could refer to it as x meters and x meters. It doesn't really matter. That's the displacement. You just need to know what it is. Distance from undisturbed position. So the undisturbed position is this baseline over here. That's the point where the wave is stationary, like stationary, like there's no movement at when it's over there. That's the undisturbed position, the original position, if you may. And that is what it looks like. Our third one, let's pick another color, is our amplitude, which is the max distance away from undisturbed position. Now that means the amplitude would be this. That's the amplitude. Amplitude. That's the amplitude over there as well. So these both are the amplitudes. Let's go to green for a second. Our fourth one, wavelength. I'm sure everyone knows what a wavelength is. It's the same as a cycle, basically. That's the logo for a wavelength. And length of a wave. Now from here, you can see that this is repeating. So it goes up, down, up. So up, down, up is one cycle. So one cycle, as we discussed, means one wave. So if you were to make a line over here and a line over here, that would be your wavelength. That's your wavelength right there. So one complete cycle is one wavelength. That's pretty simple. Now let's go back to red. Actually, not red. Let's keep it blue because the graph is red. Now the other stuff you need to know is period. This is time taken for one cycle to pass a point. Now what this means is that if this wave was going towards the right, and let's say we take a point here, so how long would this cycle over here take to pass this entire point? So this wave would be going towards the right, So if this was going towards the right like that, then oh, how long would the wave take to reach that point? Usually it's a fraction of a second, but of course it can be slower. If it's like a beach wave, then it takes periodically longer. Where's my mouse? Okay. Our sixth thing is our frequency. This is how many times a complete cycle passes a point per second. This is where our equation comes in. F is equal to 1 over time period, where F is in hertz. Now, what this shows is how, so if one wave takes 0.25 seconds to pass a point, that means in 1 second it can pass the point 4 times, so the frequency is 4 hertz, which is the same as saying the wave passes the point 4 times a second. Okay, all pretty good so far. Our next thing is a phase. Now this is the most confusing out of everything. A phase is a measurement of the position of a certain point along the wave cycle. Okay, now what this means is, let's say we had the wave continuing, so we had that going up and then back down like that. Now that's our one cycle, right? Now if we say our cycle was starting here, this is the start and this is the finish, and half of the phase would be halfway across the wave. So a half phase difference would mean that two waves are approximately half of a wave out of sync from each other. So if something was half phase behind another wave, it would look like, so if this is our wave 1, if the red is wave 1 and blue is half phase difference, so lambda over 2, since that's the wavelength divided by 2, that's the phase difference, so half phase difference, our thing would look something like, ooh, just a moment. So our new points would be halfway across. So if this was our old wave and this is where it touches, that's our new point. Oh, that's our new point. That's our new point. That's another new point, and that's the peak. So it's underneath that. That's the peak. So it's above that, and of course below as well. But I think that should be enough to construct the wave. So if we go there, touch it there, go down there, touch it there, go up, and keeps on going, except for that last part. It's fine. But as you can see, it's halfway ahead of the other one or behind, whichever way you want to see it, and that's the phase difference. So the phase is the measure of a position of a point's position on the wave. That's it. I'll do the same one because it's the same topic. Phase difference, on the other hand, is how far a wave is behind another. So if you're playing games, for example, and you have these things called packets, which are sent to the server, and you're sending two packets, but one packet is slightly behind another packet, but it's between another packet. So let's say we have a packet of data, another packet of data, and another packet of data, and this stream continues. But we have two streams of data where this one is roughly halfway behind the other one. It means it is halfway behind the other stream. That means it's out of phase by half of the stream. So yeah. Okay. Amplitude is done, frequency, wavelength, speed. Yeah, wave speed. Okay. Our next thing is reflection. Let's change color. Apologies. Reflection and refraction. Okay, now what is this? Well, reflection is the wave bouncing back after hitting a boundary. In its simplest terms. Now what this means basically is, let's say you took a ball, you have a ball, and you throw it against a wall. What happens to the ball is that it hits the wall and then it bounces back. Same happens to a wave, except the wave hits the wall and it gets reflected back to the direction it came from. Or if it came at an angle, the opposite angle of where it came from. That's all reflection is, so I'll write that down for a second. Next up we have refraction. This is the change of direction when a wave enters another medium. The change of direction when a wave enters another medium. What does this mean? Well, let's say you have a plane. Excuse my drawing, but a quick plane. You have a plane and it's flying, right? Let's say there are no clouds over here, clear skies. But over here, as it flies, it enters an area with a lot of clouds. Now that means the plane has to slow down a little bit, but since it has slowed down a little bit, it will change its direction. It will go a bit higher or a bit lower. If it had no flaps, of course, because a wave has no flaps, and it's solely on the direction it sends, and as soon as it enters a different medium, it will get a bit refracted, which means that it will change a bit direction, so that's called refraction. It's the same as when a bullet is shot into water, you immediately see as it's slowing down, it starts to fall back down due to the friction and the mass around it that it's trying to cut through. But as it falls down, it is falling down as it is changing its speed. So that happens same to a wave. So as soon as a wave enters another medium, it starts to change its direction because it speeds up or slows down. That's refraction and reflection. Oh, one more thing I forgot to mention. For frequency, when we do hertz, the units is 1 cycle per second. So one is which is equal to a hertz. So yeah, frequency over time period, and yeah, okay. Okay. Oh, one that's a bit. Oof. Okay. What's next? The biggest part. Wave equation. What is the wave equation? Well, it links together wave speed It links frequency and it lends wavelength. It links wavelength. These are the three things that are used in the wave equation. Now, what is the wave equation? Well, wave speed is equal to wavelength times frequency. In normal terms, wave speed is represented by a c or a v. It can be either or. C is usually used for the speed of light, and v is also the wave speed, but in our equation it's c, I believe. So c is wavelength, wavelength times frequency. And that's it. C is equal to wavelength times f. CVF lambda. And that is your answer. That is your equation, which is also a derivative of wave speed is equal to distance traveled over time taken. So instead of the time taken, we turn it into a frequency since it's 1 over, so that becomes up. Distance traveled is turned into wavelength because that is the size of one length, of one cycle of the wave, which gives us the idea of how long it is, and you get that equation. So we'll remove this. That was just for understanding. Now, if we had an example, a wave with uh, with wavelength 420 meters travels at 125 meters per second. Find the frequency. Well, pretty simple if we just plug in the values. Travels at 125 meters per second. Okay. Wavelength, 420. Okay, times f. Now we just have to find f, so we rearrange, divide both sides by 420, so 125 divided by 420 gives us, off the top of my head, I think it's 0.3 hertz. And we've done it to two significant figures. You could do it to 3, then it would be, it would still be 3 because rounding. Now make sure that all the values are same, so meters and meters. If it was in nanometers, you'd have to convert it, so 5 nanometers would be 5 times 10 to the power of minus 9, I believe. Or you'd have to just switch to the correct value. So if it was millimeters, you'd have to do 5 times 10 to the power of minus 3 to get it back to normal. Plus 3. So some simple questions. Does wave carry matter or energy? It carries energy. The relationship between frequency of a wave and its time period, that is, frequency is equal to 1 over time period, because that's how many it passes a point per second. The units of frequency is hertz, displacement is seconds, displacement is meters, and amplitude is also meters, which is the maximum magnitude of displacement, so the maximum distance away from undisturbed. And the equation for c, lambda, and f is this, wave speed. So I will actually highlight this since it's used very widely across all of physics AS exams. So that's the most important one. And that's everything.